Your biggest chips don't fail in the fab. They fail on the balance sheet when defects kill yield and slow launches. Split the die, and you can turn the same wafer into more usable parts, lower risk, and ship faster. A chiplet is a small, purpose-built slice of a larger design that you combine with others in one package. A die-to-die interconnect is the short, high-speed link that moves data between those slices without leaving the package. Here's the setup. Lithography tools can only print a region of limited size in a single exposure, known as the reticle limit, which caps how big one die can be. The decision is to partition the big design across multiple chiplets. You separate compute, memory controllers, and input-output blocks, then reconnect them with dense on-package wiring. Mechanically, this works because short links on a silicon bridge or interposer behave more like on-die wires than like long circuit board traces. Distances shrink from centimeters to millimeters, which slashes delay and lets you run many lanes in parallel at moderate speed. The basic cause and effect is simple. Smaller dies see fewer defects per die, so a higher fraction of them pass test, which means more good parts per wafer. Yield drives cost because you pay for wafers, not for good chips. If one giant die survives half the time, while 4 small dies survive about 4/5 each, the effective cost per usable compute slice can drop by roughly a third after assembly. You also gain flexibility. Binning, sorting each die by speed and power, lets you pair fast compute tiles together for premium models and match mid-grade tiles for mainstream ones. SKU agility follows. With a shelf of compatible tiles, you can dial core counts, memory width, and I/O lanes without a new monolithic mask set. Now the trade-offs start. Every boundary you create adds latency and protocol overhead compared with a single fused die. Latency is the first bottleneck. On-die wires move signals in fractions of a nanosecond, but hops across a package at a few nanoseconds, which can stretch critical paths if you are not careful. Cache coherence is the next decision point. If cores on separate chiplets share a unified memory view, the coherence traffic can eat bandwidth and increase tail latencies under contention. You can mitigate that with larger last-level caches per chiplet, smarter prefetching, and NUMA-aware placement that keeps data close to the requesting cores. But each technique trades complexity for performance and works best when software is tuned to the layout. Power is another cost because of the PHY, the physical interface block that drives the on-package wires. PHY energy scales with speed and lane count, so a big mesh of links may burn a few watts per edge and tens of watts in aggregate. Packaging complexity rises too. A multi-chip module needs extra layers for power delivery and clock distribution, tight placement tolerances, and thorough testing to ensure the assembled stack behaves like a single device. Assembly yield matters as much as die yield. If you need 8 good tiles to make one product, one bad tile can scrap the whole package unless you design in redundancy or accept partial configurations. Thermal design gets trickier because hotspots multiply and sit closer together. You must spread heat across the lid, balance thermal interface materials, and avoid starving inner tiles of airflow. Interconnect bandwidth becomes a design budget rather than a free good. You have to decide how much width to allocate between compute tiles, between compute and memory controllers, and out to the I/O hub. Bandwidth fights with latency in subtle ways. A very wide link at moderate speed is efficient for streaming, but the serialization depth and buffering can worsen small, random accesses. The cache hierarchy is your lever. Keep hot working sets inside each tile, push shared data to a near memory slice, and reserve the fattest links for bulk movement instead of fine-grained ping-pong. Context length in modern models adds pressure because key value caches balloon as sequences grow. When that traffic crosses chiplet boundaries, per hop delay can cap tokens per second even if raw math is ample. Reliability also shifts. Shorter links and smaller dies can improve overall defect tolerance, but more parts mean more opportunities for a marginal contact or aging issue unless testing screens for it. Despite the costs, the payoff is real when you match partitioning to workload. For example, splitting a very large die into 4 smaller tiles can turn a wafer that once yielded dozens of good chips into a wafer that yields many more usable tiles, trimming effective dollars per teraflop by about a third after assembly and binning. Why it matters to training and inference is direct. When you can ship more parts at stable power, you scale clusters faster, and when interconnects are sized to the model's traffic, You avoid stalls that turn into idle accelerators and higher bills. Latency-sensitive inference feels the boundaries first. If the last hop to memory crosses a package link, the slowest requests in a batch can stretch, so you design the graph to keep hot tensors local and send cold tensors over the fabric. Training cares about throughput and utilization. If the die-to-die mesh delivers about 1,000 gigabytes per second between compute and memory tiles, the math units stay fed. If it delivers only a few hundreds, the pipeline bubbles and energy per token rises. Next is the roadmap on packaging. In 2.5D, chiplets sit side by side on a silicon interposer with very fine wiring, which is great for bandwidth but adds cost and interposer yield risk. In 3D stacking, one die sits on top of another with vertical conduits, which crushes distance but makes heat removal harder and complicates testing of buried layers. Expect cache on compute stacks to lead because they offer short, regular traffic and modest power per bit. Standards unlock the mix and match promise. A common die-to-die protocol, a shared PHY spec, and agreed test hooks let different tiles from the same ecosystem speak the same language without custom glue. Standards also support lifecycle wins. Vendors can update a memory controller tile or a security tile without respinning the entire compute die, while customers get clearer interoperability and faster time to volume. Supply constraints still decide the pace. Advanced packaging capacity, known good die testing, and interposer sizes all gate how quickly chiplet products scale and how widely they reach. Energy footprints will stay in the spotlight. If the added PHY and coherence overhead eat too much power, chiplets lose their edge. So designers are pushing shorter links, lower swing signaling, and traffic shaping to keep joules per bit down. The result, when executed well, is a portfolio that moves faster and wastes less silicon. You get more granular products from the same wafer starts, you ship variants on the cadence of tiles rather than monolithic reprints, and you can place the newest process only where it pays off. Here is the principle to remember. Chiplets pay off when yield risk and product flexibility outweigh the latency and power overheads of stitching small dies together. And here is the quick checklist. If your design is near the reticle limit, your wafer yields are volatile, and your roadmap needs many SKUs split the die. If your workload is ultra-latency sensitive with tight coherence and modest area, stay monolithic. Subscribe for more Future Forge.